Welcome back. This is lecture 36. So we were discussing the transmitter chain, right? So we finished off the mixer part, at least the upconversion mixer part, where from you take your baseband signal and upconvert it to around FLO, right? And we also saw how to ensure that using I and Q combinations you get rid of the images and so on and so forth. So the next part is to understand, once I have everything in the upconverted version, how do I radiate it out, right? So the radiating out the signal is essentially done by obviously by the antenna, but like before, we will assume that the antenna is a 50 ohm load, correct? And so the whole purpose is to figure out how to deliver the requisite amount of power to a 50 ohm load, right? So the next part of this course deals with power amplifiers. Now, how is a power amplifier different from an actual amplifier or a voltage amplifier? Note that the emphasis is on power. Okay. To give you a trivial example, let's say you have a common source amplifier and at a very low frequency, so that the input impedance is 0, right? So what is the power input to this what is the amount of power that you are drawing from the source? Power in is 0, right? Because Zn is infinity, right? At very low frequency, that is true. And let's say I know that your V out over V in, small signal, I am not showing the bias, is approximately equal to 1. So is this a voltage amplifier? Clearly not. So not a voltage amplifier. But what is the power out? So this current out is Gm times V in, right? So let me also show the biasing, because I have shown the biasing on the VDD side. So the incremental current is Gm times V in, total current is Gm times V in times IDC, but the incremental power output will essentially be Gm times V in square, Gm square V in square, that is the current that is going into RL, right? So what is the power gain? That is P out by P in. This is infinity, because you are not drawing any power from the input, but you are getting power at the output, right? So this is a power amplifier. Right now, in principle, you are never going to get infinity, because you are always going to extract some power. Your input impedance to your MOSFET is never 0 and never infinity. We saw other models before that there is a resistive component to it, there is a capacitive components to it, but this is a very idealized scenario. The point that I wanted to emphasize from this first couple of minutes of discussion is the fact that in order to get a power amplification, you don't necessarily require a voltage amplification. That is number one, right? So number one is voltage amplification not necessary to get power amplification. Okay, so that should be obvious. The second thing, the reason we are talking about power amp is we would like to deliver, the emphasis is on delivering a lot of power, right? So the emphasis is on, by the way, the short form of power amp is PA, and we are going to call it PA very often. Emphasis in PA is to deliver large power. Right, so now large and small are obviously relative terms. Now what is large, what is small in this case? So I have to give you some benchmark, right? So typically the power levels, expected power levels, typical P out is of the order of 0 dBm, 10 dBm, 20 dBm, 30 dBm, and so on. And I have written so many terms because it depends on the protocol, right? Sometimes you should be able to appreciate this. Let's say you are using a cell phone to communicate, and you know that whenever you speak into the cell phone, the radiation that that comes out of the cell phone through the antenna is ultimately aimed towards the tower. If the tower is let's say a kilometer away from you, then the cell phone obviously has to radiate a lot of power. In certain protocols, the power output required from this cell phone is as high as 30 dBm, right? But on the other hand, if you are using IoT applications where you have small devices which are being controlled through remote control and so on, then you probably don't require such high power output. So hence, depending upon what is the requirement, you tend to categorize these. I mean, you can have all these different sorts of power levels. But the key thing to note is that these are all going up by factor of 10 dB, the way I have written it out. But it's not necessary that they have to be always increasing by factor of 10 dB. The part that I wanted you to appreciate is that even though what does this increment of 10 dB mean? So 0 dBm essentially means 1 milliwatt, 10 dBm means 10 milliwatt, 20 dBm means 100 milliwatt, and 30 dBm means 1000 milliwatt or 1 watt. So you can have power amps required. You might be asked to design power amps which have a requirement of delivering power from as varied a range between 1 milliwatt to 1 watt, right? So that naturally creates some interesting design challenges which we are going to talk about, right? Another important thing that we need to understand is that in PA, the power output is assumed to be delivered to a 50 ohm load, which is an antenna. Okay, so now in practice, an antenna will never give you a perfectly 50 ohm load, because the antenna is also has to be designed, right? So it will never be a 50 ohm load. It will always have some imaginary impedance and some variation from 50 ohm also, right? And even if you design a perfectly balanced antenna which gives you 50 ohm, and you deploy that antenna in the field, then depending moment the antenna radiates something, if there is a blocking surface nearby, or some car goes ahead, cuts through the line of sight through which the antenna is propagating, so there will be a reflection from the interface. Moment you have a reflection from the interface, from a transmission line theory, we understand that the impedance is no longer 50 ohm. There can be deviations, right? So you can have imaginary components also. So, but assuming all of these are true, we will still go ahead, at least in this course, we'll go ahead by assuming that the antenna is 50 ohm, right? Because the principles of design still holds, just that you'll have to calibrate for non-50 ohm resistances or non-50 ohm impedances once you design an antenna using a 50 ohm assumption, right? So that's another assumption we'll keep in mind. Now the next thing that we should keep in mind is that if the 50 ohm load cannot be changed, and we want to deliver these different types of power levels, then what is the amount of voltage swing that we are talking about, right? So if you have a 50 ohm impedance and you want to deliver certain amount of power, which means the voltage swing Vp, if it's a sinusoid of amplitude Vp, then for 0 dBm, and this is Vp. So if you have 0 dBm, then then what is the relationship between power and Vp? So your power is essentially Vp squared by 2R, R is 50, so Vp squared by 100, right? So if we do the math, then 0 dBm will be approximately equal to 310 millivolt, right? You can approximate 300 millivolt also if the calculation becomes slightly tedious, right? So back of the hand calculation, you can approximate to 310 millivolt. Similarly, if you go to, let's say 10 dBm, right? 10 dBm means 10x in terms of power, which means it will be approximately 3.3x in terms of voltage. So 10 dBm will not approximately, if you do the math, it will come out to be 1 volt of Vp, right? And so on, right? And if you go to again 20 dBm, so this will be approximately 3 volt of Vp and so on. Now this is Vp, correct? Similarly 30 dBm means approximately 10 volt of Vp, right? So now if you are using transistors in which the maximum supply voltage itself is 1 volt or maybe 2 volt, and you want this output swing across the resistor to be of the order of 1 volt amplitude, which means 2 volt peak to peak, which means that this becomes difficult to implement, right? So that is what we are going to address next. Okay, so before we go into discussing about how to deliver these kind of power, so let's see what is the simplest power amplifier stage we can build. And if you think about it, the only stage among all the single transistor topologies that we know of from our basic analog circuit courses, the only stage that can give us gain is essentially a common source amplifier. All other stages which can give gain are also some variants of the common source amplifier, right? So we'll stick to common source amplifier and then take it from there, right? Okay, so what's the issue? So let's assume that we have a common source amplifier which is driven by a constant current source, and you have bias and voltage sources and everything, and you have a load which is RL, to which you have to deliver that power, right? Whatever 0 dBm or 30 dBm or whatever, you have to deliver power to that RL. So clearly I cannot connect this to RL directly, because since RL is a modeled impedance, it's one of the side is assumed to be grounded, which means that I have to AC couple the load, right? So let's say I AC couple the load, and let's assume that C tends to infinity and all, right? So we assume this, okay, and this is the current source IDC, VDD, and so on. So now if you want to deliver, let's say if I go to this table, let's say I want to deliver, I don't know, maybe 10 dBm power, so which means that I would want the voltage swing here to be equal to plus 1 volt. If this is 0 quiescent, so this is minus 1 volt. So I want this voltage swing to be peak to peak to be 2 volt. And if the capacitor is AC shorted, which means that I am expecting the voltage swing here to be also around 2 volt, right? Correct? So now if you are using a voltage supply which is like barely 2 volt or less than that, then this clearly is not possible. In this case I have assumed ideal current source, but in principle current sources are also made using transistors and so on, right? So this seems to be a problem, right? And not only that, it's not necessary that the transistors that we have here might not be able to sustain that swing also. So the transistors, as it turns out, they have a breakdown voltage because you have these junction capacitances which are made out of thin oxides, right? If I am talking about the junction capacitance between the gate and the channel, or if you talk about the PN junction, there is also a junction capacitance, and each of these junctions have a breakdown voltage associated with it, right? If you give too much of an electric field between these two junctions, then there can be a punch through of the carriers to the dielectric, and you can have breakdown of the transistors. So which essentially means that you will always have some maximum limits of swing that you can sustain. So now you see you have a problem. The problem is we want to have a lot of swing here, but we cannot sustain a lot of swing here. So what can we do? So I need some sort of swing transformation, right? While ensuring that the power transformation, power delivery does not really get affected. Now, what type of circuit do you think we are looking for? We have done this before. We are essentially looking for a transformer, right? So if instead of connecting this directly, if I connect this through a transformer, right? So let's say this is 1:n. Then if this is RL, then the impedance looking here is RL over N squared, correct? And then I can do all sorts of common source amplifier and all, right? This is AC coupled, right? So you can use a transformer to reduce swing. Why? Because right now, if the swing here is, so I should say 2 Vp. So the power delivered is Vp squared by twice RL. This should be equal to the power that is going in from this side. So if the swing here I say is Vd, right? Vdp, that is a swing, drain swing, peak drain swing at peak amplitude swing at the drain. So this should be equal to Vdp square by RL by N squared, right? So which essentially means this goes by twice goes, which means that your VDP is equal to Vp over N, correct? And this should make sense because it's a transformer, right? The swing at one side is basically N times the other, or N time 1 over N times the other, right? So in this case, it makes sense that the swing will reduce. So clearly, using a transformer, we will be able to push in as much power as we want with as much amplitude across RL as possible, while ensuring that the voltage swing across the at the drain of your transistor remains small. Now, if I want to push in lot of power, then obviously I have to ensure that your N is high, right? In order to ensure the swing at the drain of your transistor remains low, right? So the key takeaway is, second key takeaway is, for a power amplifier to deliver large power while ensuring the drain voltage swing rather, is within check or within limit. Now this limit can be a breakdown limit, or limit can be that power supply limit, or whatever. Within limit, use a transformer or some sort of matching network or an impedance transformation network. Or a matching network. I mean, all are the same thing, different variation of other, with high end. It's basically an appropriate end, right? So given that you know that the whatever is the maximum swing I can have at the drain, right? If I know that a priori and I need a higher swing at the load, then that ratio of the swing sets the impedance transformation ratio, and that's what we are in, right? The trivial example that we had done before is this. So if I had to up convert the impedance, right? If I want to increase the impedance, you have to reduce the voltage division. You have to increase the voltage division, right? You have to reduce the voltage across RL. If I had to, on the flip side, if I have to down convert the RL, we have to reduce the current division, right? So, or rather, have to increase the current division. We have to reduce the current that flows into the RL, which means that we would probably need to have a C here and an L here to ensure that this impedance ratio is appropriate, right? So here this is, or RL over Q squared, correct? Where Q is essentially the ratio with which the current is getting divided, right, which is omega CR between capacitor and RL, right, omega CRL. So if you want larger swing, you basically have you use this kind of contraption as an impedance transformer, and you can go ahead with the design, right? Okay, so now that seems simple, but whenever something seems too simple, then you should question that there's probably something hidden which I am not telling you, and there are, but one of the main problems of one of the main specifications of PA is because we are talking about delivering, I mean, hundreds of milliwatts of power, efficiency of the PA, power efficiency of the PA becomes important, right? So your power efficiency becomes important. So your eta, it becomes important, which typically is defined as power delivered by the power consumed, right? Or typically it's power PDC, basically the amount of power you are consuming from the DC source. Okay. Now, why is this important? Why is eta so important in PA? And we did not really talk about eta so much for the other blocks. The reason is bulk of the power of a transmitter is consumed by the PA, right? You are talking about power of the order of tens and hundreds of milliwatts, whereas your LNA mixer and everything were probably consuming few milliwatts, maybe 10 milliwatt or 20 milliwatt or anything. So if not done properly, the amount of power that you are consuming in a PA can be forget about the thing that if not done properly, the amount of power that you need to deliver at a load can be multiple times of the amount of power that you consume in the rest of your transceiver. Okay, which essentially means that if you have, let's say you are trying to deliver 100 milliwatt and you have an efficiency of 50%, which essentially means that you have to burn 200 milliwatt of power. As simple as that, correct? So which means that the additional 100 milliwatt of power is getting wasted as heat, isn't it? But your rest of your transceiver is not even taking few tens of milliwatts, right? So which essentially means that if you can save power in PA, you will do yourself a huge amount of favor by reducing the overall power budget of your system, right? So hence power efficiency in a PA becomes super critical. Now there are multiple ways of defining efficiency in a PA. This is the brute force classic definition of efficiency. There are other metrics of efficiency. I will talk about one of them. So it is called power added efficiency, or PAE, which is P delivered minus power in divided by PDC, right? So what is power in this case? So again, till now we have not really talked about power in. So obviously your power, for delivery of power, you have this transformer and everything here, and you have some matching network and stuff here, and you are delivering P in here, right? So in the earlier example that I showed you, your P in was 0 because we are talking about low frequency, right? But be mindful of the fact that this is the frequency is at around FLO, correct? So which means there is a capacitive load. Now capacitor cannot really dissipate power, so you should, if you have a capacitive load, not necessary that it is going to dissipate power. But we have an RG also, right? There is a channel resistance, there is a gate resistance, which is actual resistances. The series combination of this RG and the capacitance is going to dissipate power, right? So that is from is that power coming? That power is coming from whatever is driving this PA, right? So if you recall, there is a mixer before this. That mixer is probably now driving this PA, and hence you are drawing power from the mixer. You are not drawing power from its PA's source. Hence this metric of power added efficiency. Okay, so that is number one. And number two is, it is quite often in designs you are going to see that PAs are not on the same chip as the rest of the mixers and all, right? So this is important. When non-negligible power is drawn from the source or from the previous stage, right? So this is important here, and it is also important when PA is a standalone block and not a part of the rest of the transceiver. It's basically, I'm saying it's not on the same chip. If it is not on the same chip and you have a PA, right? So which means that moment you connect it, you will connect it to long transmission lines, at least on the input side. So there will be maybe a long transmission line coming here and so on, right? Which means you will need matching. Moment you need matching, you will not have capacitive load, you are going to have some sort of resistive load, right? Which means that you are going to draw power from the input. So you end up becoming, in those circumstances also, PAE becomes important. Now your question might be, why do I need to have a standalone block? Why cannot be in a part of the transceiver? So there can be multiple reasons. One of the most common reason is because it is supposed to deliver a lot of power, which means you cannot waste power, which means the output of the PA cannot have long routing, right? Because if the output of the PA has long metal routing, then naturally it will have resistance and you are going to burn power in the resistance, and a large current flowing into the metal, large current flowing into the resistance is going to cause a lot of unnecessary power consumption. So hence what it is generally done is PA is physically placed very close to the antenna. Okay, so if the PA is physically placed very close to the antenna, and it's not necessary that the rest of the transceiver needs to be placed close to the antenna. So in that case, often the entire transceiver chain is broken down into everything but the PA, and then maybe a pre-power amplifier and a PA, but they are they are somewhere down the signal chain, and the PA is placed strategically close to the antenna, right? So in those cases, obviously you are going to have a separate PA block. As it turns out, in most of the cell phones that we use, most of the PAs are separate PA blocks, and they are placed close to the antenna. Hence this power added efficiency metric also becomes important, right? Okay, so there is an antenna here, so I should write antenna is close by. Okay, so the next thing to talk about is efficiency, right? I have been harping on that efficiency in a PA is important. So let's see what is the efficiency that we can get using a classical common source topology, and then we'll see what else can be done, right? So let's look at the classical common source amplifier. And let's say we have this configuration, and I'm not showing you the balun and all, and I'm not showing you the transformer. Let's assume that this RL is a transformed impedance, right? So if that is the case, then let's say there is an IDC that is biasing, and how the IDC is biasing is also not shown here, because obviously if you push in a current source from top onto a current into a transistor without any negative feedback, then this, you don't know how it will get biased. So but let's assume that the biasing has been done by auxiliary circuit somewhere, right? So we are not concerned about that. What we are concerned about is that let's assume the bias has been set up. What is the maximum efficiency that we are going to get? Okay, so for that, the first intuition that we should understand is that in order to maximize efficiency, right, we obviously have to operate it under maximum output power condition, right? Because the DC power that this contraption is drawing is basically VDD times IDC, correct? So amount of current I am drawing from the supply is kind of fixed, right? It is VDD times IDC. So in order to increase efficiency, I'll have to ensure that what is the maximum power that I can deliver to the output, right? So before I go there, let me ask you one question. So let's say I have a source here, and I have a source resistance here, RS, and I have a load resistance, RL. if I ask you, if I ask you, what is the condition on RS? Let's say RS is a variable resistor. What is the condition on RS for which I will be able to deliver maximum power to the to RL, right? The question is, what is max, what is the condition on RS for max power across RL? So clearly this condition is RS equal to 0, right? Because if RS equal to 0, the entire voltage drops across RL, and you do not, and basically voltage power across RL is the voltage squared by R. So hence it's a no-brainer, right? So the reason I emphasize this is that we should not confuse it with the case where given an RS, what is the condition on RL? So that's a different condition where RL is variable. Here RS is variable, right? So that's an important distinction to make. Okay, so now let's proceed with whatever we were discussing. So now the condition is we would like to ensure that the maximum power gets delivered to RL. So under which condition the maximum power is getting delivered? Now obviously we understand that the input is swinging, right? Which means that the output is also swinging, correct? So let's further assume that with simplifying assumptions, the threshold voltage is 0 volt, correct? Which means that your overdrive can be as low as 0 volt, i.e. V overdrive min can be 0 volt, right? So these are all simplifying assumptions, which means that VDS min can be 0 volt, correct? Okay. If that is the case, then, by the way, I mean, threshold voltage to be 0 volt, threshold voltage 0 volt is not necessary for this. I mean, let's assume that V overdrive min is 0, right? So, okay, just to simplify the assumption, because I would want, if I do not simplify this assumption, then I'll have to ensure that this minimum is above 0. Right, so that's the only assumption I am making right now, and you will see that what will be the impact of that later on. Okay, fine. So if I make the assumption, then what we end up with, which essentially means that if let's assume that this guy here also swings from minus Vp to plus Vp. I'm interested to find out what is Vp in terms of IDC and RL, correct? Otherwise, I will not be able to find out the efficiency. So how do I find out what is Vp in terms of IDC and RL? What is the condition? The condition is when I am hitting a minima at the output, obviously I am hitting a minima here also, right? At the drain of the transistor. And what is the minimum voltage of the drain of the transistor? The drain can go to with the condition of VDS min equal to 0, which is 0 volt, right? Because we are assuming that the transistor is always on, right? It's barely going to linear region around 0 volt, right? So basically, when your transistor is, when the input is around maxima, the output is around minima, and around that condition, we are saying that it is barely going to 0 volt. Now you might say that if the input is it has a significant amount of amplitude, then the linear region condition need not necessarily be 0 volt, which will be correct. But again, we are making another assumption, is that gain is high. Assumptions is voltage gain is high. It's large. Why is this assumption necessary? This assumption is necessary because we are basically assuming that input swing is small. Basically, I am neglecting the input swing. That's all I am saying, right? So these are the simplifying assumption, and you should understand that all these assumptions will only help us increase the possible output swing, right? So even after doing this simplifying assumption, if we get a limit, then that will be the absolute maxima we can go to, right? So that's the assumption, that's what we are trying to hit at, right? Okay, fine. If that is the case, when input increases, output goes to 0. That corresponds to the 0 at the that corresponds to negative Vp at RL level, right? Okay. So now, when what is happening when the input goes negative, right? When the input is at its minima, right? When the input at its minima is at its minima, the transistor is turning off, right? Let me redraw. So when the input hits the minima, then your transistor is turned off, right? Input is minima. Assume that you have biased it just above threshold, and as the input swings slightly below threshold, the transistor turns off. That's the minima, right? Which means that all the current is now flowing into this IDC is flowing into RL. Correct? So this is when the input is at its minima. We are talking about this part of the input, right? We're talking about this crest of the input. Around this time, all the IDC is flowing into RL, and hence I am getting a maxima at the output. So if IDC flows into RL and it creates a maxima, that is this crest, or rather the maxima. So what will be this maxima be? So ultimately this also looks like this, right? So this maxima will be equal to IDC times RL, which is essentially peak. Okay? So what did I find out? I found out Vp in terms of IDC and RL. So what is the power delivered? Is Vp squared by twice RL, which is IDC squared RL squared by twice RL, right? So basically IDC squared RL by 2. Okay. And what is the power consumed? How do I know what is the power consumed? So in order to find out the power consumed, I have to find out, all I need to find out is how much is the voltage that is changing across IDC. Correct? Because see, I do not know VDD. Correct? I mean, if you have an ideal current source, VDD is not necessary. VDD can as well be 0. Correct? So essentially, I'm trying to figure out what is the voltage change across IDC. If I know the voltage change across IDC, then I should be able to find out what is the effective power, right? Power that I am consuming, right? So what is the voltage change across IDC, or rather what is the voltage across IDC? So the voltage, if I assume this, if I just check the voltage VDS, so what is VDS? So let me draw it here. That would be more useful, right? So where is VDS going from? I am going from 0 volt to twice Vp, right? Because this 0 corresponds to minus Vp, and the peak to peak is twice Vpp. So I am getting the VDS is going from 0 to twice Vpp. So what is the power that is getting dissipated? It's basically the current times the P dissipated is IDC times the voltage, that is the VDS average. And what is the average VDS? What is the average VDS? It goes from 0 to 2 VP. Average is VPP, correct? So basically this is IDC times VPP, which is IDC times VPP is IDC times RL, so IDC squares times RL. So eta becomes, your efficiency becomes power delivered by power dissipated, which is 1 over 2, that is 50%. So assuming all things that we assumed so far, that is, I mean, the swing is almost, output is almost going to 0 volt, which will never be the case. You will have to keep a overdrive voltage at that. We're assuming the gain, voltage gain is also very high. That is, the transistor always remains in saturation with only small amount of input swing, right? So that will also not be the case. Voltage swing will not be very high. So your input will swing, which means that you have to keep some voltage head, some more buffer for the transistor to swing. So even with these conditions, the maximum voltage, maximum power efficiency that you are going to get is 50%. Correct? So these type of amplifiers are called class A power amplifiers. These are typically called class APA. These are called class APA because if you see that during the entire cycle, cycle of the input and the output, the transistor is always on, right? So hence it's called a class APA, correct? So as it turns out, in a class APA, the maximum efficiency that you can get is 50%, not more than that. And in fact, you are also not going to get 50%, you are going to get much lesser in reality, because the assumptions that we took, right, will not be valid in reality. Okay. So now the next question that you should ask me is, what about IDC? How do I get this IDC? So in analog circuits, it's difficult. It's not very straightforward to get IDC because you have to have current mirror and all and everything. But fortunately in RF, we are operating at multi-gigahertz frequencies. So in those frequencies, inductors are good, which means if I have a sufficiently large inductors, which is also often called a choke, right? So this is, let's say, L, large L. Sometimes in Professor Lee's book, he calls it a big fat L, BFL, right? So it need not necessarily be a big fat L, but it's we also call it a choke if it is a big inductor which is placed outside the chip, which cannot be accommodated on chip. But anyhow, depending on which frequency you are using, you can have a large L, sufficiently large L, that is omega times L should be much larger than the resistor that you are driving. Then all for intents and purposes, you can assume it to be a current source. And if you do that, then this kind of helps you to realize a class A PA with an inductor. Now the question is 50% efficiency, which means half the power I am wasting, and without even considering anything else, right? Is that good enough? And as it turns out, in most cases it is not. So there has to be other ways of going about fixing this issue. So now, what is the root cause of this 50% efficiency? The root cause of this 50% efficiency is, if you think about it, in one input cycle, the load is going into the RL and delivering an output power. In the other input cycle, the load is, you are essentially pulling all the current out through the transistor, right? So basically 1/2 cycle only you are effectively using to deliver power, and the other half cycle you are basically giving a bypass path for the current path to go through. So that's what essentially is happening, right? And because of that, you are severely being constrained with the efficiency. So if we understand that, then all we need to understand is that maybe we'll have to reconfigure it in such a way that we only use 1/2 cycle in which the current is being fed to the load, and the other half cycle if we do not use it at all, right? We keep the transistor off in that other half cycle. So the main issue with this class A amplifier is that your power efficiency is pretty poor, right? So you are essentially losing half the power. And note that you are not losing half the power because you are doing matching or anything. This is just because you are burning half the power in the transistor and half the power in the load, right? So nothing to do with matching. So what is the solution? So if you think about it, one of the reasons this was an issue is because there was a time when when the transistor was conducting, right? There's no current that was going into the load, right? So, and in another half cycle, the current was going into the load. At that time, the transistor was not conducting. So if that's an issue, then which means that half the time you are essentially losing the power that is getting drawn by the transistor. So if that is essentially the case, then probably the solution should be that we should ensure that the transistor, if the transistor conducts only for 1/2 cycle in which the load gets the power, and then I can kind of turn it off in the other half cycle, then it is likely to give me a better efficiency, right? So such an arrangement is often done, and I will show you a simplified arrangement of that. So let's assume for the time being that I'll assume that the load is connected directly to the drain to make the points simpler, and let's further assume that this is biased and all. This is RL, right? So what I am saying is, let's assume that the transistor is biased just above the threshold voltage, right? So assume VGQ is almost around the threshold voltage, and also further assume that there is no distortion in the transistor. That is, if the VGS is just below threshold voltage, that is, the transistor absolutely turns off, and VGS is just above threshold voltage, the transistor fully turns on, and the characteristics, the GM and everything doesn't change, right? If you take this very simplistic model, then what is going to happen? Then also assume ideal distortionless transistor. Okay, so if we assume what I just said, then what's going to happen? So if the input swings, as long moment the input goes above 0, that is goes above VGQ, right, the transistor will suddenly start conducting, and the current that you are going to see, if I call this IDS, your IDS will essentially be something like this, right? Note that this is total IDS now. I'm not talking about incremental IDS, right? Because when there is no input, the transistor is off, right? So because VGQ is almost equal to the threshold voltage, that's the assumption. So this is total IDS, and for the half cycle of the input, the transistor conducts. Next half cycle it doesn't, then it conducts, and so on. Correct? It's almost one of those like half rectifier kind of scenarios, but note that this is a very idealized scenario in which I have assumed that these IDSs are the perfect. The only one half cycle has been fully clipped, and the other half cycle is perfect sinusoid of the half cycle, which by the way is never the case. But let's go with this assumption. So if this is the IDS, then the V0, if I take the V0 across RL, so V0 will be IDS times RL, which is V0. Correct? This I say is IP, that is a peak value of the sinusoid. Now for maximum efficiency, again, what do I expect? I expect that IP times RL should be equal to VDD, right? Again, because I am assuming that the overdrive voltage is 0 and so on, right? So assume IP times RL is equal to VDD. Okay. So now this is only one half cycle. What if I need the second half cycle? So what I can maybe do is then copy this same contraption, right? If this is Vi, let's say I apply minus Vi here, correct? And I have another arm which is also connected to, let's say, RL. Right? So what do I get here? If this is minus Vi, then the transistor will conduct in the other half cycle. So which means I am going to get this and this. Correct? So this will be again IP times RL, right? So if I can subtract the top from the bottom, I get a full sinusoid with amplitude of IP times RL, right? Okay. So how do I get that? So in principle, I can get that by, so basically what I am saying, I have two halves. Right? And I have to take the difference between them. Now note that this is happening at RF, so I can use inductors. So maybe some sort of transformer is a better way of going about doing it. So that's what I am going to do. So I'm going to use a balun, and I'll put the center of the primary to be equal to VDD, and I'm going to use this guy here to drive the RL. Okay. So what will be the efficiency of this arrangement, right? So in order to find out the efficiency, all we need to look at is the, so by the way, now, so what are we basically saying? We're basically saying that each of these are drawing some current ID, right? So I can find out the power dissipation from the DC current that effectively that I am drawing, and I know, if I know the sinusoidal current, then I know the power delivered. The ratio is essentially the efficiency, right? So if I go back to this structure, so from this structure I can basically find out what is the average current. So the average current of this is basically IDC. Note that this is not biased, so IDC is the average of this, is 1 over T, 0 to T by 2, because it's conducting for 1/2 cycle, IP sine omega naught T dt, right? And given that omega naught T is equal to 2 pi, if you do the math, this will come out to be IP by pi, correct? So what is the power consumption in one of these branches? So PDC is VDD times IP by pi, correct? And what is the power consumption in two of these branches? So PDC in this case is twice IP VDD by pi, correct? Okay. So for the time being, let's assume that this turns ratio is also 1:1. So just to make sure that our is simpler, which means that effectively the resistance between these two, terminals is also RL. What is the current that is flowing through this RL, right? It is basically IP sine omega T. Effectively, the 1/2 cycle I get the positive, other half cycle I get the negative, right? So effectively the entire, I am getting this IP times RL sine omega T to be the voltage across RL. So the power delivered is essentially is IP squared RL by 2. And from the argument that we had earlier, I know that IP times RL is equal to VDD, which means this is IP times VDD by 2, right? So what is the efficiency? It's basically IP times VDD over 2 times pi by 2 IP times VDD, which is pi by 4, which is approximately 78%, right? So clearly you see that in this particular configuration, where you make sure that the transistor kind of conducts in 1/2 cycle and doesn't do in another, and you combine stuffs, then you see an efficiency increase by almost 25%, and that is huge, right? Given the amount of power that a power amplifier is supposed to deliver, if you save 25% of the power, that is a significant advantage. Now what are we paying for? We are definitely paying by using distortion, right? Because here I assume that these are ideal sinusoids and the transistor turns on and off. So the thing is better efficiency, beta eta, but the problem is poor distortion, right? So as it turns out, you are always going to see in power amplifier, you are always going to see these type of trade-offs, right? So now is this an issue? This definitely is an issue. So how do we get rid of it? We get rid of it by putting filters, right? Now note that you don't have to necessarily put ideal transformers, right? You can put narrow band matching networks which can do impedance transformation as well as filtering, right? So instead of doing a matching network here, you can as well incorporate a filter. So include a filter can be a matching network plus filter, right? So in order to filter out the harmonics that are going to get generated because of this distortion. So as it turns out, in even if you do filtering in most PAs, what it is done generally done is that when you have a PA, you normally do not put the antenna directly to the PA. Right? I'm assuming you have taken care of the matching network and all. So simply because you are going to have distortion, which means that you are going to generate out of band sinusoids, and if you transmit that out of band sinusoids, you are going to probably be transmitting into a band which is not assigned to you. Right? It might be assigned to some other carrier, and you will be corrupting those bands. So for regulation purposes, you need to essentially put a filter. So another SAW filter is often put at the output of the PA, which then subsequently drives an antenna. Right? So this is used to filter out whatever is the out of band harmonics. Okay. Now, if you have the luxury of a SAW filter, even though a SAW filter is not an ideal filter, then probably you can play around with this class B kind of architecture and maybe take it one step further. So now what did we notice? We noticed that it looks like if I reduce the duty cycle from 100% to 50%, that is from class A to class B. By the way, this is called a class B powered amp. I did not mention this. This is called class B PA. If you reduce the duty cycle, it looks like you are gaining in efficiency. So the better thing might be to push our luck further, and then instead of having 50% duty cycle, we push for lower than 50% duty cycle, right? So if I push for duty cycle less than 50%, these are called class C PA. So they have an efficiency of greater than 78%. I'm not proving this, but you can do the math. It's basically the simple math as we have done till now. If you do this, you are going to see obviously an increase in efficiency, and you can go crazy, but the issue again will be you will have more and more distortion. So which means that the filter that you are going to need at the output of the PA will be bigger, probably require higher order roll off, and so on and so forth, right? Okay, fine. So let's stop here. We'll see you in the next class.